Hello guys, welcome to my YouTube channel. This is my first video. Hope all of you will like it. So without any delay, let's get started. Dark matter is a form of matter thought to account for approximately 85% of the matter in the universe and about a quarter of its total energy density. The majority of dark matter is thought to be non-baryonic in nature, possibly being composed of some as yet undiscovered subatomic particles. Its presence is implied in a variety of astrophysical observations, including gravitational effects, which cannot be explained by accepted theories of gravity unless more matter is present than can be seen. For this reason, most experts think dark matter to be abundant in the universe and to have had a strong influence on its structure and evolution. Dark matter is called dark because it does not appear to interact with observable electromagnetic radiation such as light and is thus invisible to the entire electromagnetic spectrum, making it undetectable using existing astronomical instruments. The idea of dark matter must not be confused with antimatter negative mass. Antimatter has been detected. Dark matter hypothesis has an elaborate history. In 1884, Lord Kelvin first used the term dark body in one of his lectures, and in 1906, Henry Poincaré first coined the term dark matter. Because dark matter has not yet been observed directly, if it exists, it must barely interact with ordinary baryonic matter and radiation, except through gravity. The primary candidate for dark matter is some new kind of elementary particle that has not yet been discovered, in particular, weakly interacting massive particles, WIMPs. Many experiments to directly detect and study dark matter particles are being actively undertaken, but none of them have yet succeeded. Dark matter is classified as cold, warm, or hot according to its velocity, more precisely, its free streaming length. Current models favor a cold dark matter scenario in which structures emerge by gradual accumulation of particles. This is known as lambda CDM model. Although the existence of dark matter is generally accepted by the scientific community, some astrophysicists, intrigued by certain observations which do not fit the dark matter theory, argue for various modifications of the standard laws of general relativity, such as modified Newtonian dynamics, shortly MOND, tensor vector scalar gravity, or entropic gravity. These models attempt to account for all observations without invoking supplemental non-baryonic matter. Now, the evidences for dark matter. First, galaxy rotation curves. The arms of spiral galaxies rotate around the galactic center. The luminous mass density of a spiral galaxy decreases as one goes from the center to the outskirts. If luminous mass were all the matter, then we can model the galaxy as a point mass in the center and test masses orbiting around it. From Kepler's second law, it is expected that the rotation velocities will decrease with distance from the center, similar to the solar system. This is not observed. Instead, the galaxy rotation curve remains flat as distance from the center increases. This is known as galaxy rotation problem. So, if Kepler's laws were correct, there must be some mass missing. In particular, there is a lot of non-luminous matter known as dark matter in the outskirts of the galaxy. To solve this problem, the idea of dark matter halo is used. A halo is a basic unit of cosmological structure. It is a region which is decoupled from the expansion and contains visible matter in it. The dark matter halo of galaxy envelops the galactic disk and extends well beyond the edge. To give a rough idea, our Milky Way galaxy's visible matter makes up to 5% of the total mass and the rest is dark matter. There are several halo density profiles describing the distribution of dark matter in the halo, such as pseudo-isothermal halo, NFW profile, ionosphere profile, etc. Gravitational lensing. One of the consequences of general relativity is massive objects, such as a cluster of galaxies lying between a more distant source, such as a quasar, and an observer. It should act as a lens to bend the light from this source. The more massive an object, the more lensing is observed. Strong lensing is the observed distortion of background galaxies into arcs when their light passes through such a gravitational lens. It has been observed around many distant clusters, including Abell 1689. By measuring the distortion geometry, the mass of the intervening cluster can be obtained. In the dozens of cases where this has been done, the mass to light ratios obtained correspond to the dynamical dark matter measurements of clusters. Lensing can lead to multiple copies of an image. By analyzing the distribution of multiple image copies, scientists have been able to deduce and map the distribution of dark matter around the MAX J0416.12403 galaxy cluster. Weak gravitational lensing investigates minute distortions statistical analysis of galaxies from vast using galaxy surveys. By examining the apparent shear deformation of the adjacent background galaxies, the mean distribution of dark matter can be characterized. The mass to light ratios correspond to dark matter densities predicted by other large scale structure measurements. Dark matter does not bend light itself. Mass, in this case, the mass of the dark matter bends space-time. Light follows the curvature of space-time, resulting in the lensing effect. The third, cosmic microwave background. Although both dark matter and ordinary matter are matter, they do not behave in the same way. In particular, in early universe, ordinary matter was ionized and interacted strongly with radiation via Thomson scattering. Dark matter does not interact directly with radiation, but it does affect the CMB by its gravitational potential, mainly on large scales, and by its effects on the density and velocity of ordinary matter. Ordinary and dark matter perturbations therefore evolve differently with time and leave different imprints on the cosmic microwave background (CMB). The cosmic microwave background is very close to a perfect blackbody, but contains very small temperature anisotropies of a few parts in 100,000. A sky map of anisotropies can be decomposed into an angular power spectrum, which is observed to contain a series of acoustic peaks at near equal spacing but different heights. The series of peaks can be predicted for any assumed set of cosmological parameters by modern computer codes such as CMB-fast and CAMB, and matching theory to data therefore constrains cosmological parameters. The first peak mostly shows the density of baryonic matter, while the third peak relates mostly to the density of dark matter, measuring the density of matter and the density of atoms. The CMB anisotropy was first discovered by Cobb in 1992, though this had not so good resolution to detect the acoustic peaks. After the discovery of the first acoustic peak by the balloon-borne boomerang experiment in 2000, the power spectrum was precisely observed by WMAP in 2003 to 2012, and even more precisely by the Planck spacecraft in 2013 to 2015. The results support the lambda CDM model. The observed CMB angular power spectrum provides powerful evidence in support of dark matter, as its precise structure is well fitted by the lambda CDM model, but difficult to reproduce with any other competing model such as modified Newtonian dynamics. This was the overview of the dark matter hypothesis. In the next part, we will discuss about the possible composition of dark matter and the efforts to detect the dark matter. Thanks for watching. If you liked it, then please like, comment and share the video, and don't forget to subscribe.